Welcome, everyone. Welcome to Harvard University CMSA Quantum Matter Seminar Series, a Quantum Matter in Math and Physics seminar series. We are very honored today to have a Professor Biao Lian from Princeton University. Biao studied at Stanford University under Shoucheng Zhang, and then he went to Princeton to do his postdoc. And currently, he is a faculty member at Princeton University. We are very happy to welcome him to speaking about his recent series, maybe 6 papers on twist bilayer graphene related topics. His talk today titled Symmetries, Insulator States, and Excitations of Twist Bilayer Graphene with Coulomb interaction. We are very highly anticipating this talk. And Biao, please take over. Welcome.
Okay, thanks, Juven. Yeah, it's a great honor to give a talk at Howard during this virtual time. And I really want to thank Juven and the organizers for inviting me. And I'm really happy to have a chance to talk about our recent work, which are very interesting about the correlated physics in twist bilayer graphene. So through these series of works are mainly, I will mainly cover the 6 papers we actually posted recently on our archive, titled TBG 1 to 6. And the works are mainly in collaboration with Andrew Bernwick's group and Nicholas Ragnar's group at Princeton. And basically the works gave a very interesting overall understanding of the correlating physics that has attracted lots of interest in condensed matter. And part of the motivation of our work actually also come from the the nice experimental studies from Ali Astani's group in STM, which we also participated. And we also had collaborations with Dimitri Avtov's group in Spain and Emmanuel Tudor's group in Texas, basically in testing some of our predictions. And there are more collaborations going on and really making the field very exciting. Okay, so in the first part, I'll just very briefly introduce the field of twist bilayer graphene. And in the second part, I will first talk about the single particle physics in twist bilayer graphene. So basically, we try to understand why the bands are flat and what's the topology in the twist bilayer graphene look like, the band topology. While in the third part, I will switch to interacting cases. So we basically study the effect of Coulomb interactions in such a system. And we will show that there are actually enhanced symmetries in several limits of the interacting Hamiltonian, which actually helps us to solve the problem, for the ground states, which we will talk about in the fourth part. And lastly, I will talk about also the excitations in the system, which actually some of the aspects are important for us to understand, like superconductivity, etc. Okay, let me start. Let me start by briefly introducing the field. So twist bilayer graphene is a prominent example of actually a large class of materials called moiré materials. Basically, it's from the concept of moiré pattern, a mathematical concept, which says if you stack 2 similar or exactly the same lattices on top of each other, 2-dimensional lattices like this, but with a relative twist angle, you would result, as a result, you would get a super lattice, which has a lattice constant in proportion to 1 over theta. So this enables the condensed matter people experiments to engineer actually a superlattice by controlling the twist angle. And this is the example of graphene. Which is basically the example we're talking about. So surprisingly, Bistritzer and McDonald first found that there exists a series of magic angles. Actually, the first one is given by theta equal to 1.05 degree. So at this angle, the lowest two moiré bands, actually per spin per valley, which I'll explain, becomes extremely flat, as you can see from this figure here. So the bandwidth basically goes down to 1 MeV. But if you tune the angle slightly away from this angle, like just by 0.15 degree, you find the bandwidth immediately enlarged by a factor 10 or so. So this is really a remarkable effect. So here I want to note that all these bands are also spin and valley fourfold degenerate, which we'll talk about later again. Basically, there are spin up and spin down degrees of freedom, and also there are two graphene valleys, valley degrees of freedom. So this makes actually in total 8 flat bands in the system. And actually there are Dirac points protected at these high symmetry points, K moiré. So here K moiré denotes the superlattice Berlin zone, which I call moiré Berlin zone, the high symmetry points of that Berlin zone. Okay, more interesting physics was found in 2018 by Pablo Herrero's group. Basically, they tuned the sample of twist bilayer graphene to this magic angle, 1.05 degree, and surprisingly, they indeed find very interesting interacting phases. This is soon followed by Correlated and Andrew Young's group, as well as Dmitry Avatov's group. And later, till today, there are actually already a lot of efforts from both experiment and theoretical directions. So the main messages is, as shown in this measurement done by Dim Avatov's group, at each integer number of electrons per unit cell, there are correlated insulators, which are not supposed to be there if you don't have interactions. So just recall that we have actually in total 8 flat bands, which are degenerate, fourfold degenerate in energy. And if you dope the system with a filling factor nu, so nu equal to 0 denotes the Chern neutrality, the original graphene. So if you change nu within the range of +4 to -4, you would just get a metallic state. But actually, what they found is, as a result, you actually get surprising insulating states at all integers. And also at non-integer fittings, superconductivities are generically observed. It slightly depends on sample, but this is the general picture. Okay, that's a very brief introduction to the twist bilayer graphene. So that's actually the experiment, both the theoretical and experimental work actually gave us raises several questions. So the first question, which is puzzling to us, to theorists, is that why is the band so flat at this magic angle? Okay, so let me first briefly introduce the model, the single particle model of twist bilayer graphene. So this is the model proposed by Bistritzer and McDonald, which turns out to work pretty well for twist bilayer graphene. So basically, the model is a plane wave expansion of the way of writing the model. So basically, the model can be viewed as 2 Dirac fermions. So at each valley, each graphene valley. So basically, at each graphene valleys, each layer contributes 1 Dirac fermion. So the 2 Dirac fermions actually couple with the interlayer potential, and this potential, due to the superlattice existence of superlattice, this potential is actually a periodic lattice potential with these Q vectors characterizing the moiré superlattice. And this hopping, actually, something important which we will use in the later is there are two parameters in this hopping matrix. So one is W naught, which is actually the effective hopping at the AA stacking of this twist bilayer graphene. So as you can see in the lattice, there are positions which are coincide with each other. These are called AA stackings. And the other parameter, W1, is at these points, which are called AB stackings. So, okay. So we want to understand why the TBG bands are actually so flat at the magic angle. So to calculate the band structure, actually, what the people do is we can transform the Hamiltonian into a momentum space using the plane wave basis. So this in general gives you the coupling between momentum k and k plus q. So q being the lattice vectors, the momentum lattice vectors shown here, and basically the Dirac fermion at different momentum differed by these momentum vectors would be coupled. So the Bistritzer and McDonald method for solving this model analytically, in some sense, is to do an approximation. Basically, what they do is they study the energy bands dispersions near the key moiré points of the Brillouin zone. So near the key moiré Brillouin zone, point of Brillouin zone, you actually can keep only the lowest 4 plane wave components. And this allows you to diagonalize the Hamiltonian in some approximations. And as a result, they found a 2x2 K.P model at this K moiré point, which has a Dirac fermion form with an effective velocity depending on theta. So this actually gives the magic angle. Basically, what is defining Bistritzer and McDonald's paper is if this velocity goes to 0, you would find the theta is actually 1.05 degree. And V theta goes to 0 just means the two bands are almost degenerate at Km point. So in our paper, we actually studied the single particle band structure. We defined this manifold found in Bistritzer as the first magic manifold. Basically, this condition can be written as the requirement that W1 is equal to 1 over square root 3 in units of VF k theta. So k theta being this length of the characterizing the size of the moiré Brillouin zone, and VF being the original monolayer graphene velocities. But this treatment by Bistritzer and McDonald doesn't answer the question why is the moiré band entirely flat within the whole Brillouin zone, because that K.P model only characterizes the band dispersion at Km and Km prime high symmetry points, but gamma point, for example, is still quite away from the point. So the other interesting thing is actually if you look at the band structure, originally Bistritzer and McDonald studied the W not equal to W1 case, which we call the isotropic limit. In this case, you find the higher bands are never too far away from the lowest two bands, which actually is kind of a bad thing, because if we want to understand some physics in the lowest flat bands, we would wonder whether the higher bands would contribute. But actually, if you slightly just make the AA hopping W0 slightly smaller than W1, immediately you get a gap much larger than the flat band width. So that's also something very interesting. And actually, there's an exact solution of exactly flat bands found at W naught equal to 0 by Ashwin's group, which is a very nice work. Okay, so, but we want to understand generically why this would happen. So basically, we consider the K dot P physics at gamma point. So we take a model which we call the hexagon model. Basically, if we choose the momentum center at gamma m point, we can keep the lowest 6 components of the momentum space Hamiltonian. So basically, you keep the six plane waves. And this gives you a 12 by 12 matrix, Hamiltonian matrix. In general, this would be kind of impossible to solve, but actually surprisingly at gamma m points, the 12 eigenvalues are actually solvable exactly for this model. And surprisingly, if you go to this point, W naught equal to W1 equal to 1 over square root 3, which is the isotropic limit of magic angle, you find there are 6 eigenvalues exactly equal to 0 in this approximation. So that kind of gives us an understanding why there are 6 eigenvalues very close to 0 there. So this allows us to do a 6-band K-P model in this isotropic limit with these numbers in isotropic limit at magic angle. And actually, the Hamiltonian can be casted in a C3 rotational invariant basis as this. And these A matrices are all 2 by 2 matrices that are exactly solvable. But their forms are indeed very complicated. But yeah, so one nice thing is that from this this model, we can actually find the analytical velocities at gamma point for each of these 6 bands. For example, along the gamma m km points direction, the flat bands just have a velocity 0, the 2 flat bands, while these 2 bands actually have a interesting velocity which are close to 1 but slightly smaller. And along the gamma m points, actually all the 6 bands have a dispersion. Actually, gamma m and gamma minus m would be opposite. But one bad thing about this hexagon model is we are keeping too little components, plane wave components, so that if you look at the Km point, the direct point is no longer there. And this is expected, of course, because the K.P model is expected to work only around gamma m point. But if you take one further shell in the momentum lattice, which we call one shell approximation. So here we call this A1 shell, and this is a B1 shell. You find this degeneracy at Km point, basically Dirac physics at Km point is almost recovered. It's already almost recovered at just by adding one more shell. Okay, so what we just talked about is the isotropic limit, but if we go away from that point, actually the things are still interesting. If you look at the hexagon model at gamma m points, if you're at this manifold, this relation between W1 and W naught, you still get 2 exactly 0 energy states. And these two states are basically the 2 eigenstates of the flat bands. And if you go away from this, so we call this a second magic angle, magic manifold. If you go away from this second magic manifold, actually you find the gap between these 2 eigenvalues, 1 and 2. Sorry, this is not. So the first thing is if you look at the gap to the higher bands, it's actually proportional to W1 minus W naught. So this explains why if you go to W naught smaller than W1, immediately you get a gap from the higher bands. And if you go away from this second magic manifold, the lowest 2 0 eigenvalues also become non-degenerate, and the energy separation is proportional to the difference between these two numbers.
Question?
Yeah, sure.
In the previous slide, I'm not familiar with this treatment, but shouldn't the degeneracy around the Dirac points be protected by some symmetries?
At Dirac point, yeah. So actually, at Dirac points, you would you mean at Km points? In general, it's protected by C3 rotational symmetry about that point. But as you can see, this hexagon model actually this actually breaks this C3 symmetry, because if you rotate it here, you're missing one component which we deleted. So that's why it's actually not there in this approximation.
I see.
Okay, thanks.
So suppose I start with a fully C3 symmetric model. I guess to have this degeneracy, you also need to have the C2ZT symmetry.
Yeah, exactly.
Now suppose I break the C3 symmetry, but maintain the C2ZT symmetry. I guess what would happen is the Dirac cones will move in the Boolean zone, but it doesn't get gapped out immediately. Is this expectation correct?
Yeah, I mean, that's the expectation in the exact case, but here, here you don't actually see that, because you actually also loses periodicity of the Brillouin zone, so things become more complicated. And actually, if you look at this point, about this point, it actually also breaks C to Z. So yeah, basically as a result, you don't really see a Dirac point if you actually if you go above the first Brillouin zone, the results are no longer valid. But within the Brillouin zone, we didn't see a Dirac point.
Okay, I see. So is this symmetry breaking expected to play some role even for the physics at around the gamma point?
No, at gamma point, I would expect basically these symmetries are preserved. If you look at gamma point, C3 is preserved, and also C2 is also preserved. So in principle, yeah, that's why it's a K-P model at the gamma point. It's expected to characterize the physics around gamma point.
Okay, thanks.
Okay, sure.
So for
sorry.
So I mean that the splitting at the K point, I think that you already explained, because the K.P doesn't valid there, right? Because we have the big K from the gamma point, so it's not a surprise.
Right. Yeah. Indeed, it's not a surprise. So Km would already be pretty far away from gamma m, unless you add further corrections. Actually, we will talk about this later.
Sorry, okay. I have a question. So when you add this B points, so in the one shell approximation, do you recover all the symmetries, or there are still some physical symmetries that are broken?
It's still approximated. For example, if you look at this K point, you get C3 invariant for the lowest three components, but the higher components are still not C3 symmetric. So the point is actually it's similar to what Bistritzer and McDonald did. If you keep only the three components, the degeneracy is already characterized very well. It's still not exact, but you can see it's already almost degenerate.
Okay, thank you.
Okay. Okay. So actually, basically, what we just showed is that if you go away from the isotropic limit, basically W1 and W0 are no longer equal to each other, you get two zero eigenvalues. So basically, in this case, the low energy physics is just two band. So then we can do approximate the hexagon model into a two-band K.P model. And actually, we did it to the fifth order perturbation of the higher bands in the hexagon model. And surprisingly, so basically, this gave you some complicated coefficients in front, but the two-band KLP model is just a proportional to sigma z. So basically, this means your eigenwave functions within this hexagon model approximation is independent of the k around the gamma point up to fifth order perturbation, which is very interesting. Okay, but as we just said, the hexagon model actually does not capture the key endpoints well. So in order to improve the KLP model to make it approximating also better the other regions of the closed flat bands in the moiré zone, we actually take a further improvement by including the the perturbation from this shell. And this improved KLP model then is no longer K independent. I mean, the wave functions are no longer K independent as expected. And this actually gave you two other analytical manifolds. Basically, the first one is just like a improvement of our second magic manifold, which is defined as the point where gamma m has zero bandwidth within the two bands. And this gives you a more precise manifold given by this expression. And we can also define another manifold, which by requiring that the Km point degeneracy is exactly recovered, this gives you another more complicated manifold. But surprisingly, both of these manifolds, if you look at these two functions as a function of W1 as a function of W0, their deviation from the first magic manifold is smaller than 1%. So they basically agree with each other pretty well. So this kind of answers the question why the bands are so flat near the magic angle, irrespective of W0, whether W0 is equal or smaller than W1. Basically, we find a manifold which almost have zero bandwidth at both gamma m and km. So these 2 points kind of pin the bands entirely flat in the moiré zone. Okay, now let me switch to the band topology of these flat bands. So actually, as shown by earlier studies, these two flat bands per spin per valley in Bilayer graphene are also topological, but their topology, band topology, is actually a very special one called the fragile topology, which was first come up with in Ashwin's group by Ashwin's group. So this kind of topology is special in the sense that you can add some additional trivial bands to the system. And together, actually, if you hybridize the bands, you can find a way to trivialize all the topology of these bands. I will not explain the details here, but yeah, but this is a little bit counterintuitive, but there are indeed models, and actually, Bilayer graphene is a physical model here. So in Bilayer graphene, this fragile topological index is basically equivalently can be understood as the Dirac helicity within the Brillouin zone. Basically, the flat bands come from the hybridization of two Dirac fermions from the two layers in one valley. Because they are in one valley, actually the two Dirac fermions carry the same helicity. And this gives you a non-zero total Dirac helicity, which is equal to 2. And this turns out to be the fragile topological index. So the other way to characterize this topological index is to calculate the so-called Wilson loop of the two bands. And if you look at the Wilson loop eigenvalues, they have a winding number which is equal to 1/2 the Dirac helicity, which I'll explain more about this Wilson loop later. Okay, so then the question is, if you have more bands coming down, whether the system is still topological. For example, if we go to smaller angles where actually higher magic angles can be defined, if you look at the band structure, actually multiple bands are connected to the flat bands. Actually, earlier also shown by Ashwin's group, that if you go to 10 bands, basically you add 8 bands to the lowest flat bands. I mean, not arbitrarily 8 bands, but some trivial bands. You can get a 10-band model which trivializes this C2Z T fragile topology. However, we actually showed that in this paper too, if you consider another symmetry in the system, which is actually a very precise symmetry, basically it's an anti-unitary polyhole symmetry, then the topology of this fragile topology of the Bilayer graphene becomes a stable topology. This polyhole symmetry, actually, you can see it directly from the band structure. Basically, the dispersions here are almost identical to here. Actually, and actually, as shown actually also in the Bistritter-McDonald paper, but also explicitly come out with in Andrew Bernewick's group, is that you can define a zero angle approximation under which actually the polyhole symmetry becomes exact. So with or without this approximation almost does not affect the band structure, as you can see. So this symmetry is a pretty good symmetry. And actually, because of the C2ZT symmetry in the system, which is an anti-unitary symmetry, you can define both a unitary polyhole symmetry or anti-unitary polyhole symmetry. They are just they just differ by C2ZT. So the anti-unitary polyhole symmetry satisfy an interesting property. So first, it flips both momentum and kinetic Hamiltonian. Besides, it actually squares to -1, a little bit analogous to the spin-fold time reversal symmetry.
Sorry, this new time reversal, this new particle hole symmetry, does it also flip the spatial coordinates?
Spatially, it doesn't. I think, let me see.
But it involves C2Z.
Okay. You're talking about P or C2Z?
C2Z.
C2Z. Yeah. C2Z would flip a position. But yeah. But in momentum space, they.
Yeah, but then how? So you're calling it a particle hole symmetry, but it also acts spatially, right? It's not local in real space.
Let me see. I think it's still local. So you can show actually. I think it's also in your paper. In your paper, it's P times T, but in our paper, it's a C2Z times P. So C2Z times P is a local operation, I think, in real space. If you look at the real space, am I?
Then the original P. I think it cannot involve C2Z if it is local. Otherwise, the unitary particle hole you define here is not local.
Yeah, I don't quite remember, but yeah, if I remember correctly, this P it's not a crystal symmetry, but if you look at the real space transformation, I think it's a local operator. Basically, C2ZP, as you remember, it's a K preserving operation and also unitary.
It's K preserving unitary, but it maps R to minus R.
Sorry, this is Andrei Nevedomsky. Well, there is nothing wrong with the inversion, right? Inversion is an example of a point group symmetry. It's perfectly local, since that it's defined at every position of the carbon atom.
I think what Astim says is if you consider also the position, you have to choose a center of rotation, then this point would be flipped to that point. That's not preserving R. Yeah, of course, it preserves R up to lattice lattice vector shiftings.
Yeah, I mean, the space group of the crystal is always point group and, product with translations.
Yeah,
sure. If it's a moot point or not, maybe there's more subtlety. But the only way to break C2T symmetry is, for instance, if you couple to HBN and you break AB symmetry, but otherwise, in the absence of some strange AB charge density wave, it should be preserved in a graphene.
Yeah. I think the question is not whether it's preserved here. But anyway, because I don't remember exactly, but actually we are all going to work in k-space. So far, basically this relation, we'll just go with this relation. Okay, can I proceed?
Yeah.
Okay, thanks.
Sorry, can I ask you a question on speed? So what is the statement about P? Is it that the remote bands are also particle hole symmetric, or do you care about the remote bands, or do you only care about the active bands?
Yeah, basically all the bands are particle symmetric. So you can see these higher bands are also symmetric. So in this case, for example, if you consider small angles, you can consider these set of particle symmetric bands together, and it's still a valid symmetry.
Yeah, I guess maybe the question is, why are you interested in the remote bands?
Yeah, that's because if you go, of course, the experimental hasn't been done much, but if you go to the second magic angle, which is about 0.5 degree, actually, if you look at the band structure, there are eight low energy bands in total for each spin and valley. So in that case, you might want to consider a low energy projected Hamiltonian within the higher bands as well. Yeah, so just to be general, we also included this possibility, which would be important for small angles.
But near the first magic angle, it doesn't matter.
Right. Near the first magic angle, just those two bands is sufficient.
Yeah. Okay.
Okay. Thanks. Yeah. So okay. So let me just briefly talk about the proof. So basically, this anti-unitary particle symmetry, which satisfies p squared minus 1, is equal to y minus 1. It gives a double degeneracy in the Wilson loop eigenvalues, which is similar to the Kramer pairs in time reversal case. I'll not show the detail, but basically Wilson loop is defined as if you have a Bernoulli zone, you can consider a loop along one direction of the Moiré-Bernoulli zone, and define the basically these the product of these wave functions. So this is basically, or the unitary transformation which diagonalize the Hamiltonian. You basically multiply them along this line, and this defines the Wilson loop operator, and the eigenvalue is basically mod 2 pi. So as you can see in the C2Z case, so in the C2ZT case, actually, if you have two bands with a winding number, you can add two trivial bands to the system, and upon hybridization of the bands, actually these two bands are will actually eliminate this winding number from from minus pi to plus pi, like this, by opening gaps. So this basically destroys the fragile topology. However, if you have this p symmetry, actually any trivial bands you add to the system has also if they also satisfy this p symmetry, they have to also be doubly degenerate at 0 and pi. So as a result, you can see even with the hybridizations, this winding number actually remains. So that kind of protects this topology in the system. So the nice thing about this is this shows that if we go to smaller angles, the bands are low energy bands, although become multiple, are still topological. And so if we consider some topological effects predicted for the TBG fragile topology, for example, we actually predicted affecting Hofstadter butterfly, they are expected to remain. And actually, this Hofstadter butterfly effect in the effect is observed by the Aftov's group in a 0.5 degree sample. And the reason to go to lower samples is just to allow lower magnetic fields.
So Biao, could I ask you just to clarify your statement?
Yeah.
So if I go back to how you introduced or if I follow, Adrian Paul's Ashwin's argument, they would argue that within, let's say, K theory, those low-lying active bands, they're actually topologically trivial because you could always pad them and remove the degeneracy. What you seem to be saying is that that's fine. However, if on top of this I impose this extra anti-unitary particle hole, I could make this K theory actually stable, meaning no matter what you add in terms of the padding of the bands, you still have this pi winding of the Wilson loop. Is that your statement?
Yeah, that's the statement. But but I'm not sure whether it works the same in K theory. But in the framework of Wilson loop, at least you can see it's non-trivial.
Right. And could you clarify whether that anti-unitary particle hole symmetry, is that an exact symmetry of the problem, or is it approximate?
So actually, there is a limit where it's exact, as shown by actually Jennifer Carroll's group. So if you go to W not equal to 0, let me see here. If you remember this parameter, if you go to W not equal to 0, which is known as the Carroll limit, then this symmetry becomes exact. Other than if you're not there, actually we numerically show this is about accurate, at least below 1% of the energies. Okay. Okay. Thanks for the question. Okay. Now let me move on to the interacting part. So we are interested in understanding the physics of the two-spot graphene under Coulomb interactions. So basically, our treatment is that we want to see the properties of the projected Hamiltonians within certain set of particle symmetric low energy bands. So the Coulomb interaction in general takes such a form in momentum space. Basically, these delta rhos are the doped electron density relative to the charge neutrality. And this V is just the repulsion from the Coulomb interaction. And these G's are actually moiré reciprocal vectors, basically defining the moiré-Berlin zone. So basically, if you take the original Hamiltonian, actually all the you need to sum over all these G's because they are actually from the plane wave basis of the monolayer graphene, which has a much larger momentum range. And this interaction, if you here we consider generic interaction. I think as also Oscar Vafak's paper considered. If you add a top gate and a bottom gate to the system, which is the case in transport experiments, and these gates are separated by length c, then you get a screen potential actually taking this form. Okay, so just to be general, because for lower angles, we actually have more lower energy bands. We consider the lowest 8 max bands and project the Hamiltonian into the system. So here, n plus minus 1 are, plus n and minus n are the n's conduction and valence bands. And just to remind you that we also have the spin and valley degrees of freedom. So this interaction, actually, as you can see from this, this expression can be straightforwardly rewritten into a interesting form. That this, by defining this operator, here we define a square root of this v because it's always a positive number. And this is basically the density relative to the density within the projected band relative to charge neutrality. And these form factors are given by the wave functions of the lowest bands. So you can see that the Hamiltonian is actually a positive semi-definite Hamiltonian. And actually this is actually useful for determining the ground states, as I'll talk about later. Okay, so the projected interaction Hamiltonian actually already has a spin and charge rotation symmetry U2 times U2 in just without any other assumptions. So yeah, basically because the two valleys, basically one can show that two valleys are almost decoupled. If you ignore all those terms, actually the densities are basically contributing to the projected Hamiltonian independently from the two valleys. And one can do a spin charge rotation within each spin, each valley. So this gave you a U2 times U2 symmetry, which actually preserves the electron momentum K, and has generators as shown here. So hereafter I'll use tau to denote the valley degree of freedom, and as for spin, and this zeta is for band basis. So as you can see, these S, A, B are the valley rotations, basically relative rotations between the two valleys. So there's also another symmetry, which is actually expected, which we call the many-body charge conjugation. This is defined as the anti-unitary particle followed by an exchange of C and C dagger. So that changes your electron state into a hole state. And under this symmetry, you can show that the Hamiltonian just is shifted by a constant. So this basically means that, yeah, it's a chemical potential term rather than constant. Sorry, I should be more clear. But this basically means that if you look at the physics at fitting nu and minus nu, which are symmetric about the Chern neutrality, all the physics should be particle symmetric. Okay, so actually there's an interesting limit where the symmetry gets enhanced. That is when you go to the flat band limit. Okay, before that, let me introduce another combined operation, which is C2Z times P. So if you look at the properties, their relations with the Hamiltonian, you find the anti-commute with H0. That's because particle flips your band structure. Basically, so yeah, it flips H0. But it commutes with, actually commutes with the interaction Hamiltonian. And the other thing is C2ZP actually preserves the electron momentum. So actually, as identified by Mike Zaratel and Ashwin Vishwanath's work in this paper, this symmetry actually enhances your symmetry into a U4 symmetry. And the similar U4 symmetries are also proposed in Khan Bafek's paper, and also this Su and Kotev and Yusha's paper. But those are in real space. But here we are considering it in momentum space. So this C2Z, if you go to the flat band limit where H0 is 0, then you can drop it, and your Hamiltonian is just HI. And this actually gives you additional symmetry of the system, commuting symmetry with the system, with C2ZP. And because it's a K-preserving symmetry, actually, you can use it as another generator, the single particle version of it as another generator, and together with the U2 and U2 symmetry, they generate a U4 symmetry, enhanced U4 symmetry in this limit. So basically, because P only connects the plus minus N bands, we can consider these generators just within each pair of bands. And within each pair of bands, basically the generators takes this form. So this operator and this operator are from the U2 times U2, while these two operators actually flip the valley degrees freedom. And okay, so this operator in particular is basically given by the C2ZP.
Excuse me, can I ask a question? So,
yeah.
Before you go forward, maybe I can go backward. Can we go back one slide?
Yeah, sure.
So how general is this conclusion that the physics? So here you didn't take the chiral limit, right? And okay,
right here not.
This nu to minus nu symmetry.
Yeah, this is very general. This is before you make any flat band or chiral symmetry approximation.
Yeah, and, so assume that you know very well that in experiments things are extremely asymmetric.
Yeah, it's sorry, you mean unsymmetric or symmetric?
Not non-particle hole symmetric. The coordinated
right.
positive nu. or have bigger gaps than the ones at negative mu.
Yeah, so I would say they are symmetric to the zeroth order. So here, yeah, indeed we did approximate. So like the particle symmetry, as we said, is actually not an exact symmetry. It's about 1% error if you relative to the Bistritzer-McDonald model. Also, the Bistritzer-McDonald model itself is not totally characterizing the realistic system. There will be, if you consider a longer range hopping in the graphene, in a monolayer graphene, it will break particle symmetry as well. So there are indeed higher order corrections to this, which will destroy this particle symmetry.
I mean, yeah. Experimentally, the gaps measured at positive
right
u equals +2 are much bigger typically than the ones at -2. It's
yeah,
not a
yeah.
1% difference.
Yeah, exactly. So
I forget the numbers, but it's factors of 3 or something.
Yeah. So I would say here, this statement is just within the models we considered, and we'll be studying the zeroth order physics basically in this talk. But that's a very good comment.
So what's missing in the model? So clearly something breaks this p symmetry badly in the experiments, right? So
right. Yeah. As I just said, one effect would be the higher, longer range hoppings in monolayer graphene. So basically, with that approximation, your Dirac fermions are not perfect linear dispersions, but they're also a key to the third term that would destroy the particle symmetry. It actually would also affect the wave functions. So even in the flat band limit, I think the wave functions on the electron and hole sides are different, and that would affect the interactions actually, because of the projected interactions, the coefficients actually depends on the wave functions. Yeah, that's my expectation. Okay, thanks.
Yeah, could you remind us the Pauli matrix zeta? What does it act on? Is it the AB sublattices?
Zeta, no, zeta is in the band basis as I actually written here. It's the energy band basis, but also gauge fixed. So basically, we actually gauge fixed the basis into into C2Z T invariant. Basically in general it gave you a factor, but we fixed the factor into 1. Okay, so the U4, basically this U4 symmetry can be, we can find the irreducible representations of these bases of the U4 symmetry. And this irrep basis is actually straightforward. For each pair of bands, you just linear combine the two energy band bases in this way. And one could show that each of these bands form a fundamental irrep of the U4 symmetry. So, but one different thing is for different these EY. So basically we call it EY because it's the eigenvalue of zeta y. This EY equals ±1 actually give you a relative unitary transformation between the two irreps. So so as you can see, for EY equal to +1 and -1 basically differ by a tau z, basically value rotation about z-axis. Okay, so a special case in the lowest bands, n equal to ±1, is that the two bases we just defined actually also have a topology associated with it. So this is basically because of the topology of the n equal to ±1 bands, as one can show that these bases actually defines a basis of Chern number EY equal to ±1 bands. So basically in this case, EY is just the Chern number of these bases within each valence spin, and there are 4 copies of them. So this is also first shown in Mike Zaratel and Ashwin's nice work, nice work, and also later shown by Leon Ballan's work, and we also further proved this more generically in paper 2. Okay, so then there are 2 other symmetries, limits where the symmetry gets enhanced. So which we call the 2 chiral symmetries. So the first chiral symmetry, chiral limit, is defined by W0 equal to 0, and W1 is non-zero. And this leads to a first chiral symmetry. Yeah, basically here we denote it as first chiral symmetry, but in earlier literature, it's just called chiral symmetry. So this additional symmetry is key preserving, but flips the momentum. Flips the kinetic energy, and you can show that it commutes with the interaction Hamiltonian. And actually, as I mentioned in Ashwin's earlier nice work, it shows that in this chiral symmetry, first chiral symmetry limit, you can get exactly flat bands at the magic angle. And there's another chiral symmetry which we define as W1 equal to 0, but W0 is non-zero. This is of course far away from the realistic case because W1 in general is smaller than W0, but bigger than W0. But it's still an interesting mathematical limit. So similarly, it also give you a chiral symmetry, which we call C prime, that has the same property as the first chiral symmetry. And furthermore, actually, surprisingly, we can prove that in this limit, the twist bilayer graphene becomes a perfect metal with all the bands connected with each other. As you can see, basically, there's no gap at all in this band structure. Okay, in the interacting problem, with these two chiral symmetries, either of these two chiral symmetries, the symmetry is further enhanced. The U4 symmetry is further enhanced. So in the first chiral symmetry, basically, if you make H0 equal to 0, you find you get two additional symmetries. One is C2ZP, we earlier mentioned, and the other is chiral symmetry. And this actually gave you a U4 cross U4 symmetry with 32 generators. Basically, they generate more generators. And the rep of this U4 times U4 symmetry is still given by the EY basis we just defined for each pair of bands. And for the lowest bands, this is just the Chern basis. And the generators plus minus 1 basically are for these two different U4s. And you can see that the two U4s are just acting on these two Chern bases respectively. So they don't operate on the other Chern bases. So basically, this U4 times U4 symmetry can be understood as the U4 symmetry of the Chern number plus 1 bands, the 4 Chern number plus 1 bands, and the 4 Chern number minus 1 bands. So this U4 times U4 is first shown in also in Max et al. And Ashwin Viswanath's group. Yeah, but here we actually show that in general we just generalize it to higher bands as well. So the second chiral, yeah, we can also define a second chiral flat limit. Yeah, this is a little bit unphysical because H0, as we showed, there's no flat band actually in this case. But if we still assume this, that H0 is 0, we can get a similar U4 times U4 symmetry. And the rep basis is still given by the EY basis.
Sorry, I just wanted to ask something. So you say that U4 times U4, you generalize it to higher bands, but this is only valid when H0 is 0.
Yeah. So that would be only valid for higher magic angle, for example, with a strong interaction much higher than the multiple low energy bands you have there. Yeah. So
if you bring all the other bands down to 0, this is yeah.
Yeah, of course. I mean, this is an approximation and where we start. I mean, for higher bands, you can start from, for higher magic angles, you can start from H0 equals 0 for the lowest, several bands, and then add H0 as perturbation later. I mean, if we want to consider the realistic case. Of course, we didn't study it here, but yeah, in the future, we will be interested in looking at higher magic angles.
Is there a condition then that the interaction is weak enough so that you don't mix the higher band? Because at 0 angle, basically, you have a difference spectrum, right? So you have no gap at all. So what is the strength of the Coulomb that allows to do what you do?
You mean in which limit? I didn't quite fully understood.
So, yeah. So if you have 0 angle, then it's not
okay.
Right. So there is no
right.
No gaps at all.
Yeah, but in that case, your kinetic energy will be huge actually. So that's the conventional graphene, which are usually regarded as non-interacting because the Dirac velocity is very large. Yeah, but somehow if you can lower the kinetic energy in that limit, you would also get similar results, I think.
I guess my point is that at small angle, maybe I'm wrong, but at small angle, I thought that eventually the higher bands become very close to the.
Yeah. Actually, it's tricky question how the zero angle, whether the zero angle limit is equivalent to the exact zero angle, because in exact zero angle case, you have on either AA stacking or AB stacking. But in twist bilayer graphene, if you want to define a band structure, there's always superlattice with both AA and AB stacking. So yeah, it's a little bit weird to talk about the limit of bands in that case.
Yeah, I have a question.
Mm-hmm.
So you mean like when the angle is too small, then the moiré Billion zone will be very small. At this time, you can approximate that the kinetic term is small because of the momentum is so narrow.
That's not the entire reason. So you also have the hybridization between the two layers, which also suppresses your bandwidth. That's why they are also specific angles rather than just a continuum. Some special higher magic angles.
But also the Coulomb scale goes down with the angle.
Yeah, exactly. So yeah, that's probably why. Mm-hmm.
Like the fact that it's a magic angle guarantees you a flat band, but the other bands that get squished, you have to compare them to the Coulomb scale to actually make sure that you can ignore them.
Yeah, exactly. We haven't looked into that yet, but indeed that could be the reason why people haven't found similar physics in higher magic angles. That interaction is actually weaker there. Okay.
Well, could you please help me clarify the U4 cross U4 symmetry?
Mm-hmm.
So I understand when people discuss U4 symmetry as essentially generated by the product of tau A as B, so it's essentially valley. So let's say I position myself in a given valley just for specificity. You're saying that the symmetry is actually U4 cross U4. It's as if in each valley I have an additional. So what are the generators? I know you formally write the expression there and say there are 32 of them, but what is the physical operator that gives you this extra? Is that AB sublattice symmetry?
Yeah, it's roughly speaking. Let me see. So basically, this C symmetry, this new chiral symmetry C, is basically sigma Z in the AB sublattice basis. So it's kind of flipping the basis on A, but not on B. I mean, or the other. So that could be it's basically roughly speaking a sublattice symmetry, as actually, clarified by Max Zelatel and Ashwin's group, the paper in this initial paper.
Well, maybe I can ask differently. If I look at those blue and red bands that you drew. Could you say what are the quantum numbers?
Yeah, so in generic case, the quantum numbers are just the Chern numbers. I mean, suppose we talk about the lowest 8 flat bands. As we just said, EY is just the Chern number. So basically, you can decompose the 8 flat bands into 4 Chern number plus 1 bands and 4 Chern number minus 1 bands, denoted by blue and red here. I dropped the spin here now, but basically the first U4 is the rotation within the Chern number plus 1 band, and the second U4 is the rotation within the minus 1 band, Chern number minus 1 bands. Okay, thanks. Yeah. Okay, so let me see. So okay, so then there's another limit which we can study is that if you don't have flat bands, you're still having a remaining symmetry, actually C times C2Z times P, as you can show. So in this case, your symmetry, U4 times U4, actually reduces also to U4 symmetry, but this U4 symmetry actually is different from the non-chiral flat limit U4, which can be seen from the generators. Actually, in this case, you can still define your Iraq basis in the EY basis we just defined, but you can see the generators are just a pure valley spin rotation, which does not depend on EY. So in the earlier non-chiral case, there's actually a EY here. So yeah, in this case, it actually doesn't matter whether you take the EY basis or the energy band basis. It's just a pure valley and spin rotation. And similarly, you can get the same symmetry in the second chiral flat limit, in which case you also get a U4 symmetry from just the pure rotation of spin and valley. Okay, so finally, there's actually another a little bit unrealistic limit. That is, if you make an approximation that the factors, these form factors, are k independent at all the qn plus g's, then these operators actually become commuting, and your Hamiltonian becomes an extended Hilbert model, which is just these are just a number of electrons on each moiré site in real space. Yeah, but I will not talk about more details about this. This is yeah, just to mention. And so in summary, basically we show that you can see that starting from the physical non-chiral non-flat case, by going to different limits, you can find either U4 or U4 times U4 symmetry. And there are also stabilizer code limits if you assume k independent form factors. Okay, so now let me go to solving these Hamiltonians. So actually, the different limits allows us to understand the insulating phases in observing this in the experiments. So basically, we are going to focus on the insulator phases observed at the integer fittings. So the STM, from the STM and compressibility measurements, basically people found that the interaction energy scale is about 10 to 25 MeV near the first magic angle, which is much greater than the flat bandwidth. Basically, if you go to the flattest band, it's actually just down to 1 MeV. So yeah, this is shown by Ali Astani's group and as well as Ilani and Pablo's group. So a tool we are going to use for solving the ground states at different fittings is, we know that this interaction can be shifted by constant A in this way. Basically, if we shifted the operator O, which is roughly speaking square root V times the density of the electrons, we can get still a non-negative part as shown here, and a fermion bilinear term here, and this term will just be a constant. So this similar kind of rewriting of the interacting Hamiltonian is first shown in Kahn and Buffeck's work, where they consider a real space Hamiltonian. So the nice thing about this is, if we consider a state that can be, if it happens you get a state that can be annihilated by this OQ minus QG minus this AG operator, you would find that this term contributes a zero energy, which is non-negative. So in this case, and you can show that this term also just to give you this constant AG when acting on psi. So this state would become an eigenstate of the Hamiltonian. And if we further assume a condition of the form factors, which we call the flat metric condition, basically assumes that the coefficients from the wave functions satisfy some special condition as shown here. So in this case, one can show that this O0G operator in the fermion bilinear just becomes a chemical potential term. It's just some constant proportion to the electron number. So if we consider a fixed electron number state in the system, this psi would be a ground state of the system under this flat metric condition. And actually in paper 1, 4, 5, and 6, we actually numerically showed that this flat metric condition is actually a pretty good approximation in many cases. In the larger fittings, of course, and this approximation is less valid, but actually, at least for nuclear 1 and 2, it works roughly pretty well. Okay, so we consider just the first magic angle, so we only need to consider the lowest 8 bands, which has fitting smaller than or equal to 4. So a good starting point is the first chiral limit with W not equal to 0, smaller than W1. And we go to the basically the Eurap basis or the term basis of the U4 times U4 symmetry. So in this case, the operator O actually can be shown to be diagonal in this term basis. And actually, in this case, we found this Fox state. Basically, this is basically a state with integer number of term bands occupied, fully occupied, and the other term bands are fully empty. And you can choose any of these term bands to occupy. Then you find this this Fox state actually can be annihilated by this OQ minus A operator, with A chosen as a constant, basically related to the form factor. So if the so this means this state is always an eigenstate of the Hamiltonian, many body eigenstate, and it's actually becomes a ground state if the flat metric condition is holds, or actually if it's weakly violated because the state actually is gapped. It's basically a Chern insulator. Actually, unless the higher energy states come down, it will still remain a ground state. So in this chiral flat limit, actually all the Chern band bases, all the Chern number states are degenerate. Basically, if you occupy nu plus Chern number +1 bands and nu minus Chern number -1 bands, your fitting is just related to the numbers in this way, relative to Chern neutrality. And your Chern number is basically given by the difference, which can take values from 4 minus nu separated by 2 all the way to -4 minus nu. Okay, so the physical case is actually has a non-zero W naught. So to understand the non-chiral flat limit ground states, we actually add this non-chiral interaction as a perturbation. But actually before that, even if we don't consider it as a perturbation, one can show that if you go to non-chiral case, the O operator, of course, would have a hybridization between the two term bases in each spin and valley. But if you go to even fittings, as long as you either fully occupy the both bands of spin and valley, or fully make a valley spin fully empty, you find the state is still fully annihilated by operator O minus A. So it's still an eigenstate. And in this case, you always occupy equal number of Chern bands. So the state is a Chern number 0 state. And it's actually an exact ground state if you consider the flat metric condition to be holding or weakly violating. So in a generic case with non-zero Chern numbers, we can consider the non-chiral part of the interaction as perturbation. If we consider it to order W naught squared, actually you can show that the energies for a state with fitting nu and Chern number nu C actually has an energy as given by here. So here, basically each half occupied spin valley contributes energy like this. Yeah, let me show it here. So basically, for example, this would be a half occupied spin valley flavor. And numerically, we found actually this constant U1 minus nu naught U squared, nu naught U2 is actually always positive for any W naught. Yeah, I want to also note that this U1 actually also is considered in Maxalatel and Ashwin's paper. Okay, so So this actually selects a set of U4 times U4 multiplied as the ground state. Basically, as you can see, we would prefer as little as half occupied spin and valleys as possible. So basically for fixed fitting nu and Chern number nu c, for example, in this case, the optimal case would be you make the two, this valley fully occupied and this one's half occupied. This would be at fitting nu equal to -1. And this state would have a Chern number -1. So in general, in this by this criteria, you actually find there is an energy cost proportional to the Chern number. And actually, this selects out the ground states as the Chern number +1, ±1, or 0 Chern insulator at fittings nu equal to 0 +1, all the integer fittings. Depending on whether the filling is odd or even, the Chern number would be ±1 or 0. Okay, so the other limit we can consider is the chiral non-flat limit. Actually, in this case, the perturbation energy is the opposite. Basically, each half-occupied valley and spin contribute negative energy because basically that allows the spin, this half-filled spin and valley to gain a kinetic energy. So this would actually result in a perturbation energy for filling nu as this in the optimal case. But we note that this energy is actually independent of the Chern number nu c. So actually this perturbation energy doesn't select out the Chern number, at least to the second order perturbation of H0. But actually, if you go to higher order perturbation, which we, however, we haven't done, it should all these degeneracies should be broken. But actually, we showed that in paper 6 by exact diagonalizations that actually the smallest Chern number state is still favored. For example, this is a calculation for nu -1, and this is the Chern number 0 state, and this is the Chern number ±2 states, and the Chern number 0 states is preferred in this case. Okay, so lastly, if you go to the non-chiral non-flat realistic case, actually both energies contribute. So if we take the non-chiral flat state and add the kinetic energy as a perturbation, this would select out a value polarization of the state, basically breaking the U4 symmetry down to U2 times U2. So if we consider a symmetry, a state, a non-chiral flat state with a value polarization direction, that is angle phi to the z direction. So z direction meaning it's fully polarized in value k or value k prime. Then we find the energy of the perturbation energy from the kinetic energy actually takes this form, which we find where we find three couplings, J1, J2, J3. And these coefficients are just related to the fittings and the Chern numbers. So numerically, we find that you always have J2 is much greater than J1 minus J2 greater than J3. So if you look at this perturbation energy, it actually selects an intervalley coherent state. If your Chern number is smaller than 4 minus nu, basically if your Chern number is not the highest for fitting nu, and this is basically roughly 0.05 to 0.5 MeV per electron energy gain. Well, for the highest Chern number state, when your nu c is equal to 4 minus u, we get a value polarized state. But in this case, actually value polarized state and intervalley coherent states are highly compatible, which is actually have an energy difference lower than 0.005 MeV per electron. Yeah, I want to note that for even fittings, the intervalley coherent states we found actually are the same as what is found by Max Zaratal and Ashwin Vishwanath's group. Okay, so some understanding of these. Okay, so for new, so basically the result of intervalley coherent state for Chern number not being the highest is a compromisation between the non-chiral flat ground state and the chiral non-flat ground state. So if we look at the value polarizations of the non-chiral and chiral non-flat states, actually the non-chiral flat states would have Chern number +1 and Chern number -1 bands polarized oppositely about in this valley space. That's because their U4 representations actually differ by a tau z rotation, as I mentioned earlier. But in the chiral non-flat limit, actually it just favors the direct opposite polarization between Chern number +1 and -1 bands. So one way to optimize this both energies would be to put the two vectors in plane, and that's basically why the states would be intervalley coherent. But for the highest Chern number case, actually only one of the Chern bases is occupied. So in this case, the two states actually are no different from the U4 perspective. So in this case, a higher auto perturbation is needed, and that's why basically the valley polarization and intervalley coherent are highly compatible in this case. And although the valley polarization wins slightly. Okay, so this is just repeating our conclusion. So basically for ground states, we would have Chern number +-1 or 0 intervalley coherent state at nu equal to 0 ±1 ±2. And for nu equal to ±3, where the Chern number has to be highest, there's only one choice, which is +-1. The state is valley polarized. So yeah, just to mention, our results are also verified.
Sorry, when you say higher order perturbation, did you actually compute these corrections, or you deduce this from numerics?
I used it from, perturbation in numerics. It's it's not from exact diagonalization, but it's a higher order perturbation calculation, basically to the order W0 squared T squared, T being the bandwidth.
Okay.
Okay. Yeah.
Oh, sorry, I thought in the paper you said that you only consider the leading correction and.
Yeah, actually we recently updated the draft and added the higher order corrections, which actually allows us to identify the polarization here as well.
Okay, thank you.
Okay, thanks. Yeah, okay, so just to mention that our results are actually verified also by our exact diagonalization in paper 6, that at the nucleus -3, you get a valley polarized state at small W0, and the ground state number is nu c equal to +-1, which is confirmed by a overlap calculation with the Chern Fock states. And at large W0 over W1, we do see a gap closing transition, probably to some CW or pneumatic metal phases, because the ground state momentum has some shifts. And this is qualitatively in agreement with the recent DMRG in Max Zalatel's group and also Kahn and Wafek's studies. And for nu equal to -2, we can't do a full Hilbert space calculation, but we just did the valley polarized sector. And indeed, we find in a non-chiral flat case, the ground state favors no half-occupied spin valley. But for the chiral non-flat case, the state favors maximal half-occupied spin and valley flavors, which in agreement with the perturbation analysis. And for larger W0, there without the flat condition, actually there is also some transition to our other states. Okay, so lastly, I want to, not lastly, I still have, probably I
would like to ask one more question about here, the flat metric condition. So you said earlier it's only weakly broken, but.
Yeah, so at least you can see for, okay, so the first thing is that in this calculation, it's actually not the ground state sector because the ground state sector is intervalley coherent. Yeah, the other thing is, as you can see, at least for W0 smaller than 0.6 W1, without the flat metric condition, it's still giving you the insulating ground state. And actually here, later I'll show some charge excitations, which we can see that it's actually an insulator.
But beyond the numerics, so this flat metric condition, it's equivalent to saying that the Hartree potential is constant, right?
Yeah. I mean, yeah. I also talk about Hartree-Fock as well. Actually, our excitations is equivalent to a Hartree-Fock calculation. Yeah, Juan, I don't know how much time.
Okay.
Okay, I'll just continue unless Juan stops me. Yeah, sorry for being a little bit slow. Okay, so the other effect we find is that actually the highest Chern number state would be favored by the magnetic field. Basically, this is because due to the strata formula, actually a Chern insulator would have its number of particles increasing when you add a magnetic field. So this contributes a chemical potential term actually because your electron number shifts. So in a magnetic field, you would get a approximate free energy as shown here with basically a term coming from the particle number shift due to the due to the magnetic field. So this for nuclear plus minus 1 and plus minus 2, actually we identified a first order phase transition from the lowest Chern number state, basically 0 or 1, to the highest Chern number state at a finite magnetic field. So numerically we find perturbatively these two magnetic fields are around basically 0.5 or 0.2 Tesla. And yeah, interestingly, so if we predict the Landau fans of this system, we would expect to see some first order transition to the highest Chern number states, basically 3, 2, 1, 0, sorry, in a magnetic field. And this is in agreement with the recent experiments, actually in many groups. So first shown by Arias-Dani's group in STM that in a magnetic field, these highest Chern number states arises. And also similarly in transport experiments, for example, in Dima Aftov's group. And actually more interestingly in Dima's experiment, they also showed near the fitting one, there's a hysteresis loop, which basically is kind of in agreement with the first order transitions we predicted. Okay, let me just briefly talk about the excitations. So actually the exact ground states allow us to solve for exactly solvable excitations as well. So for charge plus minus 1 excitations, if we look at an excitation of the form C dagger psi, basically it's just a one electron excitations, they actually form a closed subspace with which is just a 2x2 Hamiltonian, as you can show here. This is basically a 2x2 matrix. Just by diagonalizing this matrix, you can find the excitations. And so here is the results actually without the flat metric condition. Actually, for nuclear 0, this spectrum is just equivalent to what if you have the flat metric condition. And as you can see, this actually slightly depends on the screening lens. But for this screening lens, you see for nuclear 0 and nuclear minus 2, the states basically you get a charged gap to charge excitations up to W not equal to 0.8. And for so in chiral for non-zero Chern number states, so far we only have the exact states in the chiral flat limit. So this is the calculation shown here. So in particular, we actually showed that these charge excitations, if you just flip the whole excitations, this spectrum is equivalent to the Hartree-Fock approximation to this exact ground state psi. So this so basically these bands can be understood as a Hartree-Fock bands, which actually have a gap, as you can see, for nuclear minus 2. Okay, so in ED calculations, we actually verified that this analytical charge plus minus 1 excitations are almost the lowest charge excitations at any integer fitting nu in the chiral flat limit. Yeah, because of limitation of Hilbert space, we can't do non-chiral case, but this is actually already a very nice verification. So the only exception is charge plus 1 at nuclear minus 1 without flat metric condition. Okay, so we can further calculate actually the charge neutral excitations by just diagonalizing a one-body Hamiltonian. Basically, we can consider the excitations of form C dagger C acting on psi. And okay, so this yields a bunch of calculations, and we can analytically actually prove that the ghost modes are quadratic. And this is actually due to the fact that all the ground states are U4 ferromagnets. And we also calculate the charge plus minus 2 excitations, which are all gapped. But actually the charge plus minus 2 excitations are important in understanding the Cooper pairing in the system near the integer fittings. So basically, we can calculate the Coulomb pairing energy by examining the energy difference between the lowest charge 2 excitations and the lowest charge two of the lowest charge 1 excitations. And this is known as the Richardson criterion. And we can prove that this number for our Hamiltonian, actually without flat metric condition, is always greater than or equal to 0.
Sorry, this is for a finite size, or I mean, capital N is total number of particles in some.
Yeah, but it's supposed in infinite size. Actually, this is an analytical proof instead of finite size calculation. So,
right, but the fact that if you change, so how it's if you add one particle to an infinite system, the energy changes by 1/size, or
no, this is a total energy.
Pardon?
Yeah, this is total energy, not energy per particle. So the energy actually increases by the electron of two electrons.
I see. Okay.
Okay.
And you're saying that this okay, but this whole thing, this difference is when you increase the size, it tends to a constant. It doesn't decay to 0.
Right. It's yeah, we don't know whether it decays to 0, but we can prove it's non-negative. Yeah, so there could be, I mean, it could reach to 0, but we don't think that that's indicating Cooper pairing, because 0 energy.
Richardson's criterion he looked at, I think that was about finite size system, right? So.
Yeah. Okay. Yeah. Indeed, but yeah, we expect yeah, it's not changing. Yeah, that's a good question, but we don't know yet. Okay, so just to briefly sketch the proof, actually the two-particle interaction Hamiltonian, basically what we just showed is denoted by T, and you also have the one particle, the charge 1 excitations, Hamiltonian, and you can show this two-particle interaction Hamiltonian actually decomposes into the energies of two charge plus 1 electrons and the interaction term between them. And this interaction term T prime prime can be shown to be non-negative analytically. And due to the Wiles inequality, we have actually the minimal eigenvalue of T is greater than this, bounded by this lower bound. So basically this gave you the pairing energy, which is minimal of T minus 2 minimal of R. And actually it's a non-negative value. So actually this indicates that probably there is no superconductivity from Coulomb interaction at integer fittings, at least in the flat band limit. Actually we here require the flat band limit because we need to use the exact ground states. So the possible two-spotted graphene superconductivity mechanisms is then either you would require non-flat bands. At least we didn't prove that for non-flat bands. So, but the other possibility is that you have other pairing grooves like the phonons, which we also considered earlier. Okay, so but there are some facts actually from the experiments still suggesting a purely Coulomb mechanism is unlikely. The first is that superconductivity is actually observed at integer fittings with the increasing screening, as shown by Dima Aftov's group. And also in general, in many groups, two-spotted graphene experiments, what is found is that when the bands are flattest near the magic angle, both the insulator and the superconductivity are actually the strongest. So this means it seems that the flattest band favors a better superconductivity. This is against the Coulomb plus non-flat band assumption. So then we conclude that it's more possible that the superconductivity is actually due to some other pairing groups, like the phonons. Okay, with this, I'll just conclude. My time is actually, it's a little bit too late. Sorry about that, but lastly, I want to thank all my collaborators and questions. Thank you.
I think Joan has left, so he asked me to be the host. So first,
okay.
a very nice talk. And now we move to the question session. Okay. Any questions, please ask.
I would like to ask again about the flat metric condition.
Mm-hmm.
So how do you quantify how good is the approximation? It feels like it ignores the Hartree potential, not Hartree-Fock, just the Hartree potential, which is of the same order as Coulomb. So it's a matter of numerics whether actually it's
actually
small correction or not.
Yeah, actually that's a very good question. So so the criteria for how good flat metric condition is, so with the flat metric condition, as we said, the bands would be the ground state would be an insulator, would be an exact ground state, which is an insulator with a gap. So it's also an eigenstate. So even if you break the flat metric condition, this state, the insulator state, still remains the ground state unless other states coming down. So basically, to look at how good this flat metric condition is, you want to look at the charge gap. For example, in the Hartree-Fock approximation, and what we calculated here is basically if you look at the charge exact charge plus minus 1 excitations, you can see that up to W0 equal to 0.8, which is actually the roughly the actual value, you still get a insulating gap, which is about several MeV. Of course, it's much smaller than this value. Basically, and we also show that these charge plus minus 1 excitations are basically equivalent to the Hartree-Fock bands if you do the Hartree-Fock approximation. So so at least for this case, we expect the flat metric condition to be still valid. For nuclear -3, of course, actually the higher the filling is, the flat metric condition is badly, is broken more. So for nuclear -3 in a non-chiral limit, we actually expect indeed probably it will give way to other states, like a metallic state, for example. And actually, it's indeed the case for from our ED as well. So for large values of W0, you do see without a flat metric condition, you do see it goes to some other states, which has no overlap with the Chern insulator state.
This means that the term you throw away in the flat metric condition is not parametrically small. It's just
yeah, I agree. I mean, basically, let me see. Yeah, basically for nuclear 0, the spectrum is equivalent to if you have the flat metric condition. So you can see there's energy shifting. Yeah, indeed. Actually, at the gamma point, the main effect is at gamma point. I totally agree.
So it's not parametrically small. It's of the same order of Coulomb, and then some fillings that happens to be smaller, and so some fillings that are it's not, and it also scales with the filling.
Right. So but our criteria is basically if the energy scale is still smaller than this gap, then in the flat metric condition, then it's still a good approximation qualitatively.
Yeah, but so what I just want to say is it's not parametrically smaller, it's just smaller. Okay.
Yeah.
Thank you.
Sure. I see Oscar has a...
Yeah, Oscar, you can ask the question.
Okay, I think this is kind of to follow up the discussion that Eslam is discussing. There is a way to think about that term as being parametrically small if you think about the RG when you renormalize from higher bands. So if you stick with the particle hole symmetric setup as Biao mentioned, then W W0 is going to renormalize down relative to W1. And then you're going to end up in a basically chiral limit. And then what Biao said would then become parametrically small.
I see. Yeah. So here we simply projected the higher bands out before doing any RG. So I think what Oscar said is if you do the RG also considering the higher bands first, yeah, that probably further lowers the effective W0. Am I understanding correctly?
Yeah, that's right. That's what I'm saying.
Yeah. Okay.
But Oscar, the flat metric approximation is, I think, is independent of the chiral approximation. But
no, it's not. No, it becomes exact in a chiral limit, right, Biao?
Let me see. Yeah, but it's not exact. As you can see, in this case, this is the chiral limit. In this case, there's still a difference between flat metric condition and non-flat metric condition. But in this case, what we showed is, if you have chiral symmetry, actually even up to nucleus -3, the gap is still pretty large. So in that limit, the flat metric condition is better satisfied.
Okay, I see.
So I think in the chiral limit, the wave functions maybe are decaying quicker. With the form factors are decaying quicker in momentum separation, and that's why it's satisfied more. But it's still an independent approximation. You have to set this term to 0.
Yeah, that's basically because you have less terms in non-chiral and kind of contributes less things to the flat metric condition.
Any other question? Okay, if not, let's thank Biao again.
Okay, thank you very much.
Yeah, thanks. And let's thank everyone for coming to the talk.